Hi, this is Alex from devstories.eu. SunPy, Solar Data Analysis, Episode 3 of 12. Standard Python datetimes do not know what a leap second is. When you are timing high-energy solar transients, a missed second means your data aligns with empty space instead of the peak of the flare. That is why SunPy relies on precision timing. Many developers default to using the standard Python datetime module out of habit. Datetime is not a precision tool. It lacks the astrophysical precision and solar time format support required by SunPy. It ignores leap seconds and cannot handle specialized timescales like U-time. Instead, SunPy requires you to use Astropy time objects. To bring your varied data into this strict ecosystem, you use a function called parseTime. ParseTime acts as a universal translator for timestamps. You pass it a string in almost any format, whether it's an ISO string, a custom formatted date, or a timestamp pulled directly from an old satellite metadata header. It interprets the input and returns a robust Astropy time object. This is critical because different solar observatories format their clocks differently. ParseTime normalizes everything into a standard object that knows exactly where it sits on the universal timeline, factoring in every leap second along the way. Once your individual timestamps are precise, you need to handle durations. Analyzing a solar event requires bounding your data within an observation window. This is the purpose of the TimeRange object. A time range represents a continuous span between two exact points. You can define it by providing a start time and an end time, but it is often more practical to provide a start time and a duration. Imagine you are setting up an observation window for a solar flare. You create a time range by passing a string such as the year 2010, month 3, day 4 at 10 minutes past midnight. For the second argument, rather than calculating the exact end time yourself, you pass an Astropy unit quantity of 400 seconds. The TimeRange object absorbs those inputs, applies the correct timescale, and establishes a rigid boundary for your event. This is where it gets interesting. Now you need to analyze the rising and falling phases of that flare, meaning you want to compare the first half of the event to the second half. The TimeRange object has a built-in method called split. You call split and specify the integer 2. The method instantly calculates the exact midpoint and returns a list containing two new TimeRange objects. Your original 400-second window is perfectly divided into two 200-second subintervals. There is no manual date math and absolutely no risk of dropping a fraction of a second during the division. The standard Python datetime module is meant for scheduling, but an Astropy time object is a scientific instrument. Your temporal boundaries require the exact same strict unit tracking as your spatial data, and relying on these specialized objects guarantees your windows remain physically accurate across your entire pipeline. That's your lot for this one. Catch you next time.